So yes. Thank you. So here we are. This is team 6. So we have Michelle that he had to leave, Heaven, myself, Maria, Nevidita, and Hans, and Lars, which was not in the picture, basically. So sorry, Lars. So, okay. So the project is about the prediction of, to create a predictive model for, for actually HIV viral load actually risk in and predicting its behavior in terms of seasonalities and areas in geographical areas. So then, so this would be crucial in terms of allocation of resources and also on interventional and intervention of for political makers in terms of addressing this disease and it's in the specific for HIV progression and transmission. So how we are going to do this? And so what is well known is definitely is seasonality and how it changed during the periods during the year, and then how it changed during the around the areas in Africa, and then we will focus on the specific for Kenya. And what is also known is that there is a strong relationship between HIV progression and transmission with some other variables like meteorological variables, like malnutrition around the countries and the area itself. And those are well known also to have sort of seasonalities. So why don't explore and then see whether there is any correlation between those seasonalities, and then that can help us to understand so where be ready and go and intervene in go in intervention for HIV diffusion. So first step, of course, is finding the data, and then the reason. So the main important thing is that those other variables like agricultural variables, meteorological variables, or other variables, those are more available. They are more easy to obtain with respect, of course, to HIV data or test data, which we managed also to find some. So that's that we are sort of proud of. And so just to go quickly in the data details. So we found virus load tests at the country level, monthly based. And also another data set based on with subpopulations, so divided by gender, age subgroups. And so for meteorological, we had rainfall based from satellite images, and agriculture, where we used prices for maize and dry beans, of course. So we are still considering, and then we will, that will be part of the project to also evaluate whether the choice of those variables are actually drivers for agricultural and malnourishment in the country. So the crucial part is the development of the model, and then I will I will switch with with Hans.
Does this work? Yes. All right. So thank you very much, Maria. So yeah, the models that we were thinking of course, focused on all the data. So the subpopulation data was also very important here, played a big role in helping to predict the viral load suppression in each county or even sub-county. So what we did is actually we did a very extensive modeling procedure. So we started with a generalized linear model. We added some tree-based models on top. Then we did some gradient boosting models. And well, we also added some deep learning models. But the final result is actually the combinations of all these models, which will result in the most generalizing model. And I think if we look at the final estimation error, it's 6.2% in accuracy. So what we tried to predict was how many, or what the suppression percentage was. So suppression percentage here is determined by a viral load that is below a certain percentage. And so we tried to estimate the percentage of the population that falls below that percentage, that falls below that threshold. So threshold was 1,000, which according to the Kenyan data set resulted in suppression of HIV. So we tried to predict this percentage level at county level, and so the final model had a root mean square error of 6.2%, which is actually quite good. The way this was validated is by both cross-validation as well as a test data set which was unseen by any of the models during the training. So all right, so a bit deeper into the models. So what did we learn from the models? Well, very important things, of course. The historical data that we have from the counties based on these viral load suppression rates, of course, are very important in determining the viral load suppression rates for the next month and the month after that. But what actually caught us by surprise is that, for instance, rain from the weather data, as Maria mentioned, can also have a really big impact. And that sort of surprised us. But apparently we see several reasons as to why that could happen. What else did we see? Well, if we went through the data and we looked at these subpopulations, we also noticed that if we looked at the male and the female groups separated, we noticed that there was actually a relatively high correlation coefficient between the male and females. And more specifically, if we looked at the males at the current time, and we used that to correlate it to the female suppressant percentage in the next month, we could actually see that there was almost a 35% correlation, which is, it's not that significantly high, but it makes you wonder whether or not you can use the subpopulation indicators as early risk indicators for other subpopulations as well. All right, that's what I wanted to say. Besides, we have a few insights. Of course, the summary, and I will leave that to you.
No time for insights.
No time for
If you go to our final slide, you can explore our interactive dashboard, where you can see how this data changes month by month over a 3-year span. You can investigate it by county, and you can also see our prediction for January 1st of 2018, which was not captured by the data we looked at. Thank you.
Any questions?
Yeah, maybe I'm not sure whether you have touched the point that how you deploy your approach to the real ground. How do you deploy your solution to the country?
So what you have with our model is a fairly good prediction within the year for the cycles of high and low risk times. But of course, that doesn't take into account actual data of drug resistance and is simply a predictive model. So the next step would be to gather this data over the next 2 years. So continue to validate the periods of risk according to the indicators. And then especially validating the model by sending out people to test actual drug resistance at the times of year when our model predicts that it would be higher or lower in order to see if the model is right. From there, it would be relatively simple, as everything is, to allocate resources and plan ahead for the higher and lower risk seasons, region by region.